Okay, hey folks, we are getting into this Module 9 on spectroscopy. I am really excited to get into this stuff. Many of you know that I use various techniques in spectroscopy in my research, so I always get really excited to teach this topic. And if you're following along in the book, here I'm grabbing several different topics or chapters from Atkins. So Focus 11 includes topics 11A, 11B, 11C, 11D. So I'm just kind of cherry picking some of the more interesting information or the more relevant information to what you've all learned in your prior courses here on Humboldt. So our first learning goal is going to be largely review, no basic information about absorbance, transmittance spectroscopy, but there will be some new stuff in here related to Chem. So let's go for it. So I'm sure you've probably all seen a picture like this before, maybe even in my class. So here we have some absorbing sample in a container of path length L, typically given in units of centimeters. And some amount of light is irradiated on that sample, so we call this the irradiated beam, and some of this will get absorbed and exit the sample and move on to some detector, which I often draw with this sideways eyeball detector. And that transmitted beam will be in less intensity than our incident beams. Excuse me, that's the word I couldn't think of before. Incident and transmitted. So the transmittance then is defined as I over I naught, which will always be less than 1. So there's another way that we could quantify this, and this is through the optical depth, or sometimes it's called the optical thickness. It is a dimensionless quantity, but the idea here is this is based on a natural log, and notice that it's the opposite ratio as the transmittance. So this means the bigger the optical depth is, the smaller is the transmitted beam. So a large optical depth corresponds to a small transmittance. Now, what's important to note about this natural log is if we were to look at the beam intensity, coming in, as it goes through the sample, it decays exponentially and comes out at a smaller intensity. So it is more appropriate to describe this as a natural log as opposed to a base 10 log. So now you can see these two equations here can interconvert optical depth to transmittance, and because they're related from natural log to E, they have that opposite relationship. We could also relate the absorbance as the negative log of the transmittance, and that is very similar to our optical depth. However, this is a base 10 measurement. And that is done historically because before really the advent of computers or machines that could do sophisticated calculations, it was much easier for early spectroscopists to do things in base 10. So that has remained historically then for the Beer-Lambert law, where the absorbance can be described as this molar absorptivity coefficient. So molar absorptivity, which is unique for each molecule, the concentration expressed in molarity, and the path length expressed in centimeters. So because absorbance is a dimensionless quantity, that means the molar absorptivity will be 1 over molarity, 1 over centimeters. Now, we can make an analogous Beer-Lambert law using optical depth. And when this is done, typically this is used for more molecular scale units. So for example, instead of using molarity, we use number density, which is given in molecules per cubic centimeter. The path length is still given in centimeters. And now that means this sigma, that is our absorbance cross-section. because now, as you might guess, with the centimeters canceling one of the centimeters here, that's going to have units of square centimeter per molecule. And if we want to interconvert between these two ideas, we have to change the base of our log. So in other words, I need to divide the optical depth by natural log of 10, which is 2.303. And when I do that, or similarly, I could multiply my absorbance by 2.303, I can interconvert between my base 10 absorbance or base E absorbance. Okay, so if we keep going with this, we can see then that a useful thing to be able to do is quantify the absorbance so it can be used in Beer's law. So typically we can determine concentration. And generally when we have wide or misshapen peaks, it's preferred to integrate those peaks, which will give us the integrated absorption coefficient, usually given by this like nice lovely cursive A. And of course, we can do that over a wavelength range, or we can do that over a frequency or wave number range, depending on what our spectroscopy was given in. And similarly, as you can see, if instead we multiply that integrated absorbance coefficient by 2.303, that puts us in this molecular, not molecular scale, but molecular units. So that will set us up to be able to use the cross section. Now, in general, when we have a really, really sharp, thin peak, I'll try to draw this as sharp and thin as possible. Taking the peak height is perfectly fine, because as we might guess, in this integration, when we have a very narrow range, we're really kind of approximating our integration as a sum. And over a narrow range, that would be a sum of one single value, which would just be the peak height. But if we have a fairly wide peak or even a misshapen peak, we might not get the same linear response out of peak height. So at that point, it's appropriate to take the integrated area. Okay, so why do these peaks have width then? So we refer to this as the spectral line width. There are several factors, some of which we can control and some of which we can't. So the resolution of the spectrometer, we typically have some pretty good control over that based on what our spectrometer is. But at a certain fundamental limit, we will reach a maximum possible resolution of a spectrometer, which will give us a very thin peak, but we might not be able to go any thinner than that, depending on what the spectrometer is. So molecular structure energy levels, we have no control over that whatsoever. We just take the spectra for what it is. So things that we can somewhat control in a more reasonable way are the temperature and pressure of the sample, or of course the phase of our sample, if we choose to analyze a solid, liquid, or a gas. So the first thing that I want to talk about is Doppler broadening, which is related to gas phase spectra only. And this is based on the Doppler effect. And so as you might imagine, if we have our detector right here and our beam of light is coming in, our transmitted beam, in the gas phase, we might have molecules moving away from us, or we might have molecules moving towards us. And it will actually give an observed Doppler effect, right? Similar to when or I should say identical to when you're standing there and a fire truck goes by you, wee, right? It changes frequency as it's approaching you. So this is largely given by the temperature of the sample. And we can come up with this equation here where delta nu observed or delta lambda observed, that is the width of our peak. And then now this quantity right there, that is our peak, the frequency at, or the peak height at that frequency, right? So you'll notice here that there is, it's a Boltzmann situation there with KBT. And as you might imagine, the colder the temperature gets, the slower these molecules move, and thus the less of a Doppler effect is observed. At higher temperatures, these peaks can get much wider. Overall, this only affects gas phase molecules, and typically the resolution of a spectrometer is usually more important than this Doppler effect. All the same, for a very warm gas phase sample operating under a very high resolution, the Doppler effect will be observed. So, and then the last thing to talk about with spectral width are two factors here: lifetime broadening and pressure broadening. Lifetime broadening is related to how much time a molecule spends in an excited state. So for example, suppose we have state 1, and I'll just do this generically, and state 2. We pump up our molecules into state 2, and then we see them radiate back down to state 1. So if we were to observe the time profile of that, so I'll put time on the x-axis here, and I'll put the population of state 2 on the y-axis, we would see these states decay in some first order process. So imagine we could do like kinetics on this situation. So we would see first order decay from an elevated state down to the ground state. And that's true for any state or any phase. So this is like all phases, all states. So it could be electronic, vibrational, rotational, etc. So from this first order decay, we can get a lifetime. So that is given also by tau. I know I had tau in the previous example for optical depth, where K is our first order rate constant, right? And because first order rate constants are 1 over time, this will have units of seconds, if we quantified our time in seconds. And recall that lifetime is, like 1 over E folding of the kinetic decay. So generally, lifetimes for electronic states, so I'll say T electronic, are crazy fast, something like 10 to the minus 8 seconds. Whereas lifetimes for the rotational states, so for like microwave spectroscopy, those are quite slow, something like 1,000 seconds. So now if you look at this equation, and it's approximate, and that delta is still giving us the width of our peak, this time in units of energy, we should recognize there h bar has units of joule seconds, and lifetime has units of seconds. So that gives us a unit of a joule. And now, as you might guess, the longer our molecule spends in an excited state, the broader or more wide its peak is going to be. So this is typically why we see like atomic electronic transitions, so like visible spectroscopy on atoms, have really, really sharp peaks. So, and then the last thing to talk about is pressure broadening. And once again, we can see it's an approximate relationship here, where now Z is given by our collisional frequency in the gas phase. So, pressure broadening, that will only correspond to gas phase samples. And so that collisional frequency has units of 1 over seconds. And of course, h bar is units of joule seconds. So once again, that gives us the width of our peak. And now, as you might see, this is really called pressure broadening, because the larger our pressure is, the greater is our collisional frequency, and thus the wider is our peaks. So typically gas phase spectra are much sharper under a partial vacuum condition than under atmospheric pressure. Okay, folks, so hopefully that was a bit of review as well as learning something. I'll see you in the next video.